Hey everyone, welcome back to the channel. Today we're talking about the adapter design pattern in Python. Have you ever had two incompatible systems that you need to make work together? Well, the adapter pattern is here to bridge that gap. In this video, I'll walk you through how this pattern helps in making incompatible interfaces compatible and how you can implement it in Python with ease. Let's dive right in and start adapting. 1. Introduction. The adapter design pattern is a structural design approach that enables two incompatible interfaces to work together seamlessly. It serves as a bridge between systems or classes that wouldn't otherwise be able to communicate, allowing them to collaborate without altering their original code. This pattern is especially useful when you need to integrate new functionality into an existing system or when connecting third-party libraries to your current codebase. It simplifies interaction by adapting one interface to match another, ensuring compatibility in a flexible way. Key characteristics. The adapter pattern is all about making different interfaces work together. It provides interface compatibility by translating one interface into another that the client expects, enabling systems that wouldn't normally communicate to do so seamlessly. This pattern promotes loose coupling by ensuring the client is decoupled from the implementation details of incompatible interfaces, making the system more modular and flexible. Additionally, the adapter pattern boosts reusability by allowing existing functionality to fit into new requirements without needing to rewrite or modify the original code. 2. What is the adapter design pattern? The adapter design pattern focuses on converting one interface into another that the client expects, enabling two incompatible classes to work together. It acts as a bridge between different interfaces, allowing you to integrate new functionality into existing systems without altering the original code. This pattern is particularly useful when you want to make classes with incompatible interfaces collaborate seamlessly, ensuring that your system remains flexible and easy to extend. Real world analogy. Imagine using a power socket adapter while traveling to a country with different plug types. Instead of changing your device or the socket, you simply use an adapter to convert the plug into the right format. Similarly, in software, the adapter pattern allows one class to work with another class that has a different interface by acting as a bridge between them, ensuring they can communicate without needing to modify the original classes. 3. Why use the adapter design pattern? The adapter design pattern is essential when you need systems with incompatible interfaces to work together without changing their original code. Instead of modifying the systems, the adapter acts as a bridge, converting one interface into another. This pattern promotes flexibility, enabling classes that otherwise couldn't collaborate to integrate smoothly. It is particularly helpful for integrating legacy systems, external services, or third party libraries, allowing developers to reuse and scale systems efficiently. By using the adapter pattern, you can ensure seamless integration while maintaining the integrity and functionality of the existing systems. 4. How to implement the adapter design pattern in Python. The adapter design pattern is designed to help objects with different interfaces work together by introducing a working the wrapper that converts one interface into another. This is particularly useful when you need to integrate legacy systems or third-party libraries into your current application, as it allows you to bridge the gap between incompatible interfaces. The pattern enables you to use existing code without altering its structure, making integration seamless and efficient while keeping the core logic intact. Step-by-step implementation. This example demonstrates the adapter design pattern, a structural design pattern that allows objects with incompatible interfaces to work together. In this case, the goal is to make a European plug which operates at 230V compatible with a US socket which operates at 110V. The adapter pattern enables the system to connect the European plug to the US socket by adapting its interface to what the client, in this case, the US socket, expects. Code explanation. One European plug, this class represents the existing object with an incompatible interface. It has a voltage attribute set to 230V and its connect method returns a message indicating that it is connecting with 230V using a European plug. However, this plug is not directly compatible with the US socket, which expects a different voltage 110V and possibly a different plug shape. To US plug interface, this is the target interface that the client code expects. It defines the connect underscore to underscore us underscore socket method, which is the method that any plug connecting to the US socket must implement. However, the European plug doesn't implement this method, making it incompatible with the US socket. 3. Plug adapter. This is the core of the adapter pattern. The plug adapter class implements the US plug interface and acts as a bridge between the European plug and the US socket. It takes an instance of European plug and adapts it so that it can be used with a US socket. The connect underscore to underscore us underscore socket method adapts the European plug by internally calling the connect method of the European plug instance and adjusting the voltage in the output message to reflect compatibility with the US socket 110V. 4. Client code connect underscore device. This function expects a US plug interface object, which means it can only accept plugs that have a connect underscore to underscore us underscore socket method. Since European plug doesn't have this method, it cannot be passed directly to this function. However, the adapter plug adapter makes the European plug compatible by implementing this method, allowing the client to use it. How it works. Now, first, an instance of the European plug is created, which can only operate at 230 V and connect with the European socket. The plug adapter is then used to wrap the European plug and adapt it to the US plug interface. The adapter's connect underscore to underscore us underscore socket method transforms the European plug's connection process so that it adapts to work with the US socket. Finally, the connect underscore device function is called, which expects a US compatible plug. Thanks to the adapter, the European plug can now be connected to the US socket. Benefits of the adapter pattern. The adapter pattern is useful in scenarios where existing code such as the European plug cannot be modified directly but needs to be used in a different context with compatible interfaces. By introducing an adapter plug adapter, the original class can be reused without modification and the client can continue to work as expected. This approach adheres to the open clause principle, where existing code remains open for extension through the adapter but closed for modification. In this case, the adapter pattern bridges the gap between the incompatible European plug and the US socket by adapting the voltage interface and method calls, allowing them to work seamlessly together. This pattern is commonly used in software engineering to integrate legacy systems or third-party libraries into new systems without changing the original code. 5. Real-world use case adapter pattern in action. 1. Integrating legacy systems with modern APIs. In many enterprises, legacy systems rely on outdated protocols that don't natively integrate with modern APIs or web services. The adapter pattern provides a solution by acting as a bridge between these incompatible systems, allowing the legacy system to communicate with new systems without modifying the original code. This pattern ensures smooth integration by adapting the legacy system's interface to work seamlessly with modern services, helping businesses transition to new technologies without disrupting existing operations. Why adapter pattern? The adapter pattern is helpful when you need to integrate legacy systems with modern ones without changing the existing legacy code. It works by acting as a middle layer that translates requests, allowing old and new systems to communicate seamlessly. This pattern ensures compatibility between different systems, extending the life of legacy software without requiring costly upgrades or commit rewrites. Expanded use case. Uh, Imagine a bank with an old payment system built in COBOL that needs to work with a modern payment API. Instead of rewriting the legacy system, the adapter pattern acts as a bridge. The adapter converts the bank's old payment requests into the format the new API understands. This approach allows the legacy system to keep processing payments without any changes while seamlessly integrating modern services. It ensures that the bank can adopt new technologies without disrupting the existing operations, offering both continuity and modernization. Practical implementation. In this example, we are demonstrating the adapter design pattern in the context of integrating a legacy payment processing system with a more modern payment API. The adapter pattern is useful when you want to make two incompatible systems work together without modifying their internal structure. In this case, we have a legacy system for payment processing and a newer, more modern payment API, and the adapter acts as a bridge between them, translating requests from the modern system to the legacy system. Code explanation. One legacy payment system. This class represents the older legacy payment system. It has a method called process underscore underscore payment that processes payments. However, this method and its interface are outdated and incompatible with new system that we want to implement. The method accepts an amount and processes the payment, but it doesn't conform to the modern standards required by new APIs or client interfaces. To modern paymentify, this class represents the modern payment system. In a real world scenario, this would be the newer payment gateway or system you want to move towards. The modern system has a method process underscore new underscore payment for handling payments, which uses a different method signature than the legacy system. The client would ideally want to use this interface moving forward. 3 payment adapter. The adapter is the core component in this pattern. It takes an instance of the legacy payment system and wraps it in such a way that the client can interact with it using the modern interface. The adapter implements the method process underscore payment mimicking the modern system and internally calls the process underscore underscore payment method from the legacy system. This method acts as the translator, converting a request to process a payment through the modern API into one that the legacy system can handle. 4 usage example. First, an instance of the legacy payment system is created, simulating the old system that still needs to be supported. The adapter payment adapter is then created, wrapping the legacy system instance. The adapter allows the legacy system to be used with modern API calls without changing the original legacy system. Finally, the client uses the adapter to process payments by calling process underscore payment. The adapter internally translates this call into process underscore old underscore payment from the legacy system, making the two systems work together seamlessly. How the adapter design pattern works. In this example, the adapter acts as a compatibility layer between two incompatible interfaces, the legacy system's process underscore old underscore payment method and the modern API's expected process underscore payment method. The key advantage is that the client code doesn't have to be aware of the legacy system at all. It can work with the adapter as if it's interacting with a modern payment API, while the adapter silently handles the translation between the old and new interfaces. This allows for backward compatibility with the legacy system, enabling you to integrate old systems with new client code without changing the underlying system or the client. This is particularly useful when transitioning from an older system to a new one where a full migration might not be immediately possible. The adapter pattern ensures a smooth transition by enabling coexistence between legacy and modern systems. The use of an adapter also adheres to the single responsibility principle because it allows the legacy system to remain unchanged while the adapter handles the responsibility of translating method calls. Furthermore, the pattern follows the open close principle as the legacy system remains closed to modifications but open to extension via the adapter. This allows for greater flexibility and minimal disruption during upgrades or migrations. To cross-platform development. In cross-platform development, building applications that need to run on Windows, macOS, and Linux requires handling platform-specific APIs. The adapter pattern helps by providing a unified interface that allows the application to work seamlessly across all platforms. This means the core logic remains consistent while the adapter bridges the differences between platform-specific implementations, making the development process simpler and more efficient without altering the core functionality. Why adapter pattern? The adapter pattern helps applications work seamlessly across different platforms by adapting system-specific APIs to a unified interface. It simplifies development by providing a consistent interface, making it easier for the same code to run on various platforms. This approach also minimizes code duplication and ensures that platform-specific modifications are contained within the adapter, keeping the core code clean and maintainable. Expanded use case. Imagine a desktop application that needs to interact with file systems on both Windows and macOS while ensuring a consistent user experience. By using the adapter pattern, the application can offer a unified file handling interface across platforms. For instance, a file system adapter can handle operations like opening, reading, and writing files, adapting to games on Windows or apps on macOS internally. This approach allows the same codebase to function on multiple platforms without modifying the core logic, making the system more flexible and easier to maintain. Practical implementation. In this example, we are using the adapter design pattern to provide a unified interface for handling file systems across two different platforms, Windows and macOS. The key idea here is to allow the client code to open files without needing to worry about the underlying system specifics, such as whether the file system is using Teams or Windows or apps macOS. By implementing this adapter, we make it possible for the client to call a common method open underscore file regardless of the platform. This approach promotes code reusability and keeps the system flexible when integrating with different file handling implementations. Code explanation. 1. Platform specific classes. Windows file system. This class is specific to Windows and represents the ability to open files in the NAMPS format. It has a method open underscore temps underscore file that simulates opening a file in text format. macOS file system. This class is specific to macOS and deals with files in the apps format. The method open underscore apps underscore file represents how macOS opens files using apps. These two classes represent the differences in how files are handled on each platform. They both provide similar functionality but with different interfaces open underscore nface underscore file and open underscore apps underscore file. 2. File system adapter. This is the core of the adapter pattern. The adapter acts as a bridge between the client and the platform specific file systems. It abstracts away the differences between the two systems and exposes a unified method open underscore file to the client. The adapter's constructor underscore underscore init takes in the type of system, either Windows or macOS. Depending on the type, it initializes the appropriate platform specific file system class. The method open underscore file checks whether the file system is Windows or macOS. It then delegates the file opening operation to the respective platform specific method open underscore tabs underscore file for Windows or open underscore apps underscore file for macOS. By introducing the adapter, we allow the client to work with both file systems using the same interface regardless of the underlying system's implementation details. 3. Usage example. First, we create a file system adapter instance for Windows by passing Windows to the adapter's constructor. When we call open underscore file on this instance, the adapter delegates the file opening task to the open underscore ends underscore py file method in the Windows file system. Similarly, we create another file system adapter instance for macOS by passing macOS to the constructor. When we call open underscore file on this instance, the adapter calls open underscore apps underscore app file in the macOS file system. 4. Benefits of using the adapter pattern. The adapter pattern allows us to work with different file systems through a unified interface, making the client code simpler and more maintainable. Without the adapter, the client would have to be aware of the specific methods for each platform with one underscore interface underscore file for Windows and open underscore apps underscore file for macOS, which would lead to code that is harder to maintain and extend. By using the adapter, we adhere to the open clause principle. Our platform specific classes remain unchanged, closed for modification. But we can introduce new functionality open for extension by adding adapters. If, for example, we wanted to introduce support for a new file system, say a Linux file system, we could extend the adapter to support that without modifying the existing client code or the platform specific classes. This approach also follows the single responsibility principle since the adapter class is solely responsible for adapting the interface, leaving the platform specific classes to focus on handling file operations. In conclusion, this design pattern makes the system flexible and scalable. It allows the client to work with multiple systems without being tied to specific implementations, which is crucial in environments where different platforms, Windows, Mac OS, Linux, etc., must be supported without significant changes to the existing codebase. 3. Third-party libraries integration. Applications often need to integrate third-party libraries or services which may have different interfaces than what the application expects. The adapter pattern helps by creating a bridge that allows the application to interact with these external libraries without changing its core logic. This pattern ensures that the application can seamlessly use third-party services by adapting the library's interface to match the application's needs, making integration smooth and efficient. Why adapter pattern? The adapter pattern is useful when you want to integrate third-party libraries into an application without changing the existing code. It acts as a bridge, translating the application's requests into a format that the library understands. This ensures smooth compatibility while keeping the core code intact. If the need arises to switch to another library in the future, only the adapter would need to be updated, making the system more flexible and easy to maintain. Expanded use case. Imagine an application that sends emails through services like SendGrid or Mailgun. With the adapter pattern, the application can maintain a unified email sending interface regardless of the provider used. For example, if the app is currently using SendGrid and switches to Mailgun, only the adapter needs to be updated, keeping the core email logic intact. This approach simplifies integration with various email providers, making it easy to maintain actually switch services without significant changes to the system. Practical implementation. In this example, we are utilizing the adapter design pattern to unify the interface for sending emails through different third-party services, SendGrid and Mailgun. Each of these services provides the same core functionality of sending emails but implements it in their own way. Without the adapter, the client code would have to handle each service's specifics, which would result in tightly coupled, hard to maintain code. The adapter allows us to work with different services through a common interface, making the system more flexible and easier to maintain. Code explanation. One third-party email services. SendGrid and Mailgun are two third-party services that simulate the process of sending emails. Each class has its own method for sending emails. Send underscore via underscore SendGrid for SendGrid, send underscore via underscore Mailgun for Mailgun. Both methods take the same parameters to subject and body, but the method names and the way they are called differ. This is the core problem that the adapter pattern addresses, providing a consistent way to interact with different services. To the adapter class. The email adapter class is the solution to this problem. It wraps the email services and provides a unified interface send underscore email, regardless of whether the underlying service is SendGrid or Mailgun. This allows the client code to remain consistent and only interact with the send underscore email method without worrying about the specific service in use. Underscore underscore init. The constructor takes the service type, either SendGrid or Mailgun, and initializes the appropriate email service instance. If the service is SendGrid, it creates an instance of the SendGrid class. If the service is Mailgun, it creates an instance of the Mailgun class. Send underscore email. This is the common method that the client will use to send emails. The method checks which service is being used, SendGrid or Mailgun, and calls the corresponding method send underscore via underscore SendGrid or send underscore via underscore Mailgun. This unifies the interaction, hiding the differences between the two services from the client code. 3 usage example. In the example, two instances of email adapter are created, one for SendGrid and one for Mailgun. In each case, the client calls the send underscore email method to send an email. The adapter translates this method into the appropriate service specific call. When the SendGrid adapter is used, the send underscore email method calls send underscore via underscore SendGrid under the hood, sending the email via SendGrid. When the Mailgun adapter is used, the send underscore email method calls send underscore via underscore Mailgun, sending the email via Mailgun. This way, the client does not need to change its logic depending on the service. It always calls send underscore email and the adapter takes care of the rest. Benefits of the adapter pattern in this example. By using the adapter design pattern, we create a more flexible and maintainable system. The client code no longer needs to deal with the specifics of each email service, reducing coupling between the client and the email services. If we want to switch from SendGrid to Mailgun or add another email service like Amazon says, we can do so by modifying or extending the adapter, leaving the client code untouched. The adapter pattern also adheres to key object-oriented principles such as single responsibility principle. Each class has one job. The email adapter class adapts the interface and the specific email service classes handle the actual email sending. Open close principle. The system is open for extension by adding new email services but closed for modification. We don't need to modify existing code when adding new services. By using the adapter, we maintain consistency across different services and make the system easier to extend, maintain, and scale. The client code remains simple and does not need to worry about which service it is interacting with, promoting separation of concerns and making future updates or making future 4. Adapting payment gateways. E-commerce platforms often need to work with various payment gateways like PayPal, Stripe, or Square, each with unique APIs. The adapter pattern simplifies this by creating specific adapters for each gateway, allowing the platform to use a common interface. This means the application interacts with each payment gateway seamlessly without worrying about their differences, making integration easier and more maintainable. Why adapter pattern? The adapter pattern helps simplify the integration of multiple payment gateways by providing a unified interface, allowing the system to switch between gateways without altering the core payment logic. It reduces the complexity of dealing with different APIs, ensuring the payment process remains consistent. This pattern makes it easy to add new payment gateways, enhancing the system's flexibility and scalability for future expansion. Expanded use case. Imagine an e-commerce platform where customers can choose between payment methods like PayPal or Stripe. Using the adapter pattern, the platform offers a unified interface for all payment gateways, ensuring seamless transactions. When a customer selects PayPal, the platform uses the PayPal adapter to process the payment. If Stripe is chosen, the Stripe adapter handles the transaction, all while keeping the same interface. This setup makes it easy to add new payment options like Square in the future by introducing a new adapter without changing the core payment logic. Practical implementation. In this example, the adapter design pattern is used to unify the way we interact with different payment gateways, namely PayPal and Stripe. This pattern allows us to create a consistent interface that hides the differences between these services, enabling the client code to interact with the payment gateways in a seamless and uniform manner. The goal is to handle multiple third-party services like PayPal and Stripe without having to modify the client logic every time a new service is introduced. Code explanation. One third-party payment gateways. We have two distinct classes. PayPal contains a method process underscore payment underscore PayPal to process payments via PayPal. Stripe contains a method process underscore payment underscore Stripe to process payments via Stripe. These classes simulate external payment services. Notice that each class has a different method signature, which represents the core problem. If a client were to integrate both services directly, it would need to handle each service's unique interface. This would result in tightly coupled code, making the system harder to maintain and extend. To the adapter class. The payment adapter class is the key to solving this issue. The adapter acts as an intermediary between the client code and the payment services, abstracting the differences in their interfaces. Constructor underscore underscore init. The constructor accepts a gateway underscore type argument which specifies whether the user wants to use PayPal or Stripe. Based on this, the adapter initializes the appropriate gateway object. Process underscore payment method. This method is the unified interface for processing payments. Depending on whether the initialized gateway is PayPal or Stripe, it internally calls the appropriate method process underscore payment underscore PayPal for PayPal or process underscore payment underscore Stripe for Stripe. With the adapter, the client code no longer needs to call process underscore payment underscore PayPal or process underscore payment underscore B Stripe. Instead, it interacts with the process underscore payment method, which abstracts the underlying differences between the gateways. 3 usage example. First, we create an instance of payment adapter for PayPal by passing PayPal as the gateway type. The adapter wraps the PayPal object and provides the unified process underscore payment interface. When the client calls process underscore payment 100, the adapter translates this call to process underscore payment underscore PayPal 100, processing the payment through PayPal. Similarly, another instance of payment adapter is created for Stripe by passing Stripe as the gateway type. The adapter now wraps the Stripe object, and the call to process underscore payment 150 internally invokes process underscore payment underscore Stripe Munta. Benefits of the adapter pattern in this example. By using the adapter design pattern, we simplify the interaction between the client code and multiple payment gateways. Without the adapter, the client would need to be aware of the specific method signatures for each gateway and handle them differently. This would lead to code duplication, harder maintenance, and poor scalability. The adapter solves this by unifying the interface. The client interacts with the process underscore payment method regardless of whether the payment is processed by PayPal or Stripe. This consistency improves readability and maintainability. Decoupling the client from the payment services, the client no longer directly interacts with the third party services. Instead, the adapter handles all interactions, keeping the client code clean and simple. Extensibility: if we wanted to add another payment gateway in the future, e.g., Apple Pay, we would only need to update the adapter without modifying the client code. This adheres to the open clause principle. The system is open for extension but closed for modification. Single responsibility: the adapter class has one clear responsibility, adapting the interface of third-party payment gateways to a uniform interface. The client doesn't need to deal with the complexity of integrating multiple services. In comparison to earlier examples of the adapter pattern, such as integrating third-party services like email or file systems, this example continues the theme of providing a simplified and unified interface for external systems. The same benefits, cleaner client code, improved maintainability, and easy extension, are evident here, making the adapter pattern an excellent solution when dealing with varying external interfaces. 5. Adapting hardware interfaces in embedded systems. In embedded systems, hardware components often use various communication protocols, making integration challenging. The adapter pattern standardizes communication between the application and hardware components regardless of their underlying protocols. By using an adapter, the application interacts with the hardware in a unified way, making the system more flexible and adaptable to new hardware without changing the core logic. This pattern simplifies integrating components with different protocols, ensuring seamless communication across the system. Why adapter pattern? The adapter pattern is used to help an application communicate with different hardware components without being tied to specific protocols. It makes upgrading or changing hardware easier since only the adapter needs to be modified. This pattern offers a flexible and scalable approach for managing hardware integration in embedded systems, ensuring smooth communication between software and hardware without complex rewrites. Expanded use case: imagine a smart home system where the central controller manages devices like Zigbee lights and Bluetooth thermostats, each using different protocols. The adapter pattern creates a unified interface for these devices, allowing seamless communication with the controller. When a new device, such as a Z-Wave security camera, is introduced, the system can be easily updated by adding an adapter for the Z-Wave protocol. This ensures flexible integration without tightly coupling the system to specific hardware, making it scalable for future device editions. Practical implementation: in this example, we use the adapter design pattern to handle two different hardware devices, a Zigbee light and a Bluetooth thermostat. Each of these devices comes with its own unique interface. Zigbee Lite uses methods like Zigbee underscore on and Zigbee underscore off, while Bluetooth thermostat uses Bluetooth underscore set underscore temperature. The goal of the adapter pattern here is to provide a common interface for these devices so that client code can interact with them in a unified manner without needing to worry about their specific implementations. The Zigbee Lite class represents a smart light that operates with Zigbee protocols. It has specific methods Zigbee underscore on and Zigbee underscore off to control the light. Similarly, the Bluetooth thermostat class represents a thermostat controlled through Bluetooth, with a method Bluetooth underscore set underscore temperature to set the desired temperature. The hardware adapter class is designed to act as an intermediary adapter between the client code and the different device classes. It exposes a common interface with methods like turn underscore on, turn underscore off, and set underscore temperature. When you pass a device like a Zigbee light or Bluetooth thermostat to the adapter, it determines the type of the device and adapts the method calls accordingly. For instance, when the adapter is given a Zigbee light, calling turn underscore on will trigger the Zigbee underscore on method, which turns on the Zigbee light. Similarly, when a Bluetooth thermostat is passed to the adapter, calling set underscore temperature triggers Bluetooth underscore set temperature, setting the temperature for the thermostat. The adapter raises a not implemented error if you attempt to perform an unsupported operation on a device, e.g., trying to set the temperature on a Zigbee light. This approach makes the client code much simpler and more flexible. The client can interact with various types of hardware through a single consistent interface provided by the adapter, without needing to modify the code every time new hardware device is introduced. The adapter abstracts away the device specific logic, ensuring the client can focus on high level operations like turning on a light or setting a thermostat temperature. By using the adapter design pattern, we ensure that the system remains open to new hardware implementations while keeping the existing client code intact. This pattern proves particularly useful in scenarios where multiple types of devices or services are involved, each with a different API or interface that needs to be unified. And that's the adapter design pattern in a nutshell. I hope this video helped you understand how to make different systems work together seamlessly in this pattern. If you enjoyed the video, hit that like button and don't forget to subscribe for more Python design patterns and programming tutorials. Thanks so much for watching, and I'll see you in the next one.